Everybody in the auto industry told Toyota the same thing for the last 20 years. Burn hydrogen in a piston engine and you get a nightmare. Backfires, pre-ignition, razor-thin power bands, emission spikes that make a diesel look clean. The combustion chemistry of hydrogen is so aggressive, so unforgiving, that every major automaker who tried it in the 1990s and early 2000s quietly walked away and never looked back. BMW shelved it. Ford shelved it. The consensus became gospel. Hydrogen belongs in fuel cells, not in engines. And yet here's Toyota, in 2023 and 2024, running hydrogen combustion prototypes at endurance races in Fuji Speedway, lapping the circuit, posting competitive times, and doing it with a powertrain that the industry had collectively declared a dead end. So what changed? And more importantly, what does this mean for the electric vehicle future that every government, every investment bank, and every charging network company has already bet billions of dollars on? The core engineering problem with hydrogen combustion was never the fuel itself. Hydrogen has roughly 3 times the energy per kilogram compared to gasoline. Gravimetrically, it is a spectacular fuel. The problem is control. Hydrogen ignites at a much wider range of air-fuel mixtures than gasoline, which means it wants to burn when you do not want it to, inside the intake manifold, on the compression stroke, anywhere it finds a hot spot. Early hydrogen engines were essentially controlled explosions happening in the wrong place at the wrong time. The engineering term is abnormal combustion, and it is as bad as it sounds. What Toyota cracked through years of direct injection research, originally developed for their gasoline engines, was precision. By injecting hydrogen directly into the cylinder at exactly the right moment, under exactly the right pressure, they could control the combustion event tightly enough to suppress the backfiring and pre-ignition that killed every previous attempt. This is not a new fuel in an old engine. This is a fundamentally redesigned combustion architecture informed by decades of Formula One adjacent development applied to a problem the industry had stopped trying to solve. That is the gold fact buried under the headlines. Toyota did not discover hydrogen. They solved the control problem that made hydrogen combustion impractical, and they did it using tools developed for completely unrelated racing programs. The result is an engine that produces near-zero carbon dioxide, retains the acoustic and mechanical character of a traditional internal combustion engine, and can be manufactured using existing powertrain infrastructure. That last point is not a footnote, it is a strategic weapon. Building a battery electric vehicle requires retooling entire factories, retraining workforces, and restructuring supply chains around lithium, cobalt, and nickel, materials with their own geopolitical baggage and environmental cost. A hydrogen combustion engine can be built in facilities that already exist by workers who already know how to build engines using supply chains that already function. For a company employing 370,000 people worldwide and supporting millions more in supplier networks, that is not a minor convenience. That is an existential consideration. But here is where the thermodynamics punch back, and they punch hard. The hydrogen in those tanks did not come from nowhere. It was produced by electrolysis, compressed to 700 bar, which is roughly 10,000 pounds per square inch, transported to a refueling station, and then burned in an engine that converts roughly 35 to 45% of that energy into motion. A battery electric vehicle running on the same renewable electricity that made the hydrogen goes from grid to wheels at 70 to 90% efficiency. The energy losses in the hydrogen pathway are not engineering problems waiting to be solved. They are thermodynamic realities baked into the laws of physics. Every conversion step destroys useful energy, and hydrogen combustion has more conversion steps than any competing technology. So why is Toyota still doing it? Because they are not betting that hydrogen combustion wins on efficiency. They are betting it wins on infrastructure, on geography, and on political reality. There are regions of the world, large parts of Southeast Asia, Latin America, and rural North America, where building a dense charging network for battery electric vehicles within the next 15 years is not realistic. Where industrial hydrogen production already exists near ports, refineries, and chemical plants. Where the cultural and economic relationship with the internal combustion engine runs so deep that a direct transition to battery electric is a political non-starter, not just a consumer preference. Toyota is building a bridge, not a destination. And the bridge is designed for the parts of the world the Silicon Valley EV narrative tends to forget exist. Here is the question worth dropping in the comments. If Toyota scales hydrogen refueling infrastructure to match today's gas station network by 2035 and gets combustion efficiency above 45%, does the thermodynamic disadvantage still disqualify it Or does real-world accessibility beat laboratory efficiency every single time? Because that argument is happening right now inside boardrooms and energy ministries, and the answer is going to determine what sits in your driveway in 20 years. For the kind of analysis that keeps you ahead of those decisions before they become headlines, join us and never get caught flat-footed.